Good afternoon, everybody. So today I'll be focusing a little bit different from the earlier two talks. We'll try to go into a little bit more details on the Hadoop and especially the RDMA technology of InfiniBand and how you can put these things together to get the good performance and scalability. So as we have been hearing in the today's presentation, so if you take a look at all the modern data centers, of course in the front end here, we have a lot of these components, MEM-HDFS, MySQL, HBase, etc. And the back end here, where we are focusing on the data analytics, especially the offline data analytics. So this is where like the Hadoop with its components like HDFS, MapReduce, and Spark are being used, and that's what will be the focus of this talk. So as we know, like the Hadoop has moved from like 1.x to 2.x series, but at the same time, the common components are still remaining like the HDFS, the basic MapReduce model, and also the RPC. So those components are still the same, and in the 2.x, we are having the new yarn framework. Now, if you take a look at a little bit more details of this HDFS, I think we heard several talks. Basically, it has like two big components, like the name node, which stores the file system namespace, and the data nodes, which store the data blocks, and then the MapReduce, where the computation is taking place. And even though like these frameworks have been adopted and are being used, as we are hearing in this conference, if you take a look at two components here, the first component is a lot of these have been developed with Java. This is for the platform independence and portability. The second one is that it uses sockets, and this is what will be the focus from onward. Like if you are using sockets, it is good, but at the same time, you don't get good performance and scalability. So that's what I'll try to focus a little bit later. And now, of course, we have the new Spark architecture. We also heard about that. So this is for the iterative machine learning, interactive data analytics, the Scala-based design, and based on the RDDs. And here also the original Spark design is again based on the socket. Now these come from the Hadoop side. So now let's see what is happening in the HPC side. I think if many of you might be knowing, HPC is growing dramatically in the last several years, both trying to achieve high performance computing as well as big data computing. And the components, if you see within these systems, like you take any of these large scale top 500 systems like Tiahana 2, Titan, Stampede, Tiahana 1, we of course have multi-core, many-core technologies, and a lot of these are using this remote direct memory access, or called RDMA, which started with InfiniBand and gradually moving into other technologies like Rocky, iWarp, etc., and of course like SSDs and accelerators. So these components are coming for these modern systems. Now this shows the chart from the top 500 list. Some of you might have seen it. This is based on the June 2014. Out of the top 500 systems, if you see now, there are 223 systems use InfiniBand. And just on the top 50 also, there are 25 such systems. And the largest one is at the Texas Advanced Computing Center, the Stampede. And it has actually not only the Xeon multi-core, but also the Intel Xeon 5, which is the many-core, and also InfiniBand. And this has almost like 500,000 cores. Okay, so that's the kind of systems, commodity systems are being deployed. So this is a dense chart, but it shows like all different kinds of networking stacks and protocols are available these days for commodity cluster computing. On the left-hand side, we have the sockets CAN. So that means if you have an application or the middleware, it is written with sockets. So it can go through either like a 1 gig, 10 gig, 40 gig, or even over InfiniBand, it can use a mode called IP over IB, which is TCP/IP emulation over InfiniBand, or you can do some of these 10, 40 gig TCP offload engine. But on the right-hand side, this is where a lot of stacks have started moving. So for example, here the applications in the middleware, instead of being written with sockets, you try to rewrite it with a lower level networking layer called VERFs. And that is the VERFs layer, which actually supports the RDMA interface. And then that goes through the user level communication protocols and the RDMA, and let's say it is running over InfiniBand, so I'll call it IB native. So as we go later in the talk, we'll see a lot of performance comparison between the traditional 10 gig or let's say IP over IB and then this RDMA native, and you will see how much additional performance and scalability you can achieve if you can rewrite your applications or middleware using these VERFs. So with that kind of a thing, let me spend a little bit of time saying what are the challenges. If we want to really move this kind of a middleware to this RDMA or technology, what kind of challenges do we face? And then I'll introduce this high performance big data HiBD project. My group has been working for the last 2 years. And then I'll go into some case studies using HDFS, MapReduce, and Spark, how much benefits you can achieve for different kinds of benchmarks and applications. And also I'll try to take a look at not just the traditional Hadoop cluster, but let's say the modern HPC clusters. They have like different kinds of file system like Lustre. So the question is, can we use RDMA based designs on those clusters? And if so, what kind of benefits we can have? And then I'll try to wind up. So if you take a look at this RDMA technology over the years, especially for the HPC, as you know, MPI, which is the message passing interface standard, so that is the common middleware all these modern HPC systems use. So RDMA technology has been very widely used for MPI, and also the parallel file systems like Lustre or GPFS. If you see, they have native RDMA design for InfiniBand, and broadly they deliver excellent performance. I'll show some sample numbers. So these days you can get like MPI level node to node of less than 1 microsecond latency. And also like bandwidth wise, you can get under 100 gigabits per second. And more important, these modern networks with RDMA can allow you to do this kind of communication with very low CPU utilization, like around 5 to 10%. So that means when you are running your application, you have almost like 90 to 95% of the CPU cycles are left for your application. So you get very good overlap of computation and communication, and you get not only performance, also you get good scalability. So this is the project. Some of you might be familiar. This is the MPI project from my group. We started almost the day one of InfiniBand. When the InfiniBand was coming in 2000, we started working. And over the years, this is an open source project. It has been very widely used these days by more than 2,000 organizations in 73 countries. And it's also being enabling a lot of these top 500 clusters I showed earlier. So we had a lot of expertise on how to move this kind of middleware to InfiniBand. So since last 2 years, we started asking the questions, can't we do the same things for big data, especially for Hadoop? So here it shows some sample numbers. If you take a look at like all different technologies like adapters from Mellanox or QLogic with different kinds of platforms have come. The left-hand chart is showing the half round trip. That means if I send a message from like one node to the other node, half of round trip, that is the typical latency. And you see the latency these days is around very close to 1 microsecond. In fact, for some platforms, we go below 1 microsecond. And on the right-hand side is trying to show the bandwidth. That means the rate at which we can pump data from one node to the other node. So here you will see it's like 12.8 gigabytes per second. So if you do a multiplication by 8, it is 100 gigabits. So now with all these commodity networking technologies, you can actually get this kind of performance. So with that kind of a background, we ask the question saying, what is the bigger challenges? Let's say if we take a look at all these advances in multi-core, many-core, networking technologies, storage technologies. So I call this like a supply side. That means these technologies are coming to us. And if you take a look at the big data at the top, let's say you have some applications or you have some benchmarks like Sort, Terasort, etc. So we need to take all these capabilities and deliver the performance at this layer. So that is the goal. But then these are written with some middleware. Here we are focusing on the Hadoop and Spark. And these are written, as I indicated earlier, they're written with sockets. So our first goal was to find out, like, is the sockets good enough? Or if not, can we actually try to replace that with something like RDMA and then see what kind of benefits we can achieve? And of course, to do that, we need to design communication and I/O libraries with all these different components like point-to-point, threaded model, I/O file system. Of course, there are other challenges, orthogonal challenges like QoS, virtualization, fault tolerance, etc. So in the last 2 years, primarily we have focused on asking the question saying, can we move the sockets to other protocols, and then how much benefit can we achieve from here? So here, to abstract it up in a very simplistic manner, so this is like if you see the applications are written with the sockets, and if you take a look at a little bit closer, you will see that the sockets are not designed for high performance, especially the stream semantics. Often there is a mismatch for upper layers, and typically with the RDMA network, there is something called a zero copy protocol, and that you cannot really achieve well with sockets. So what we ask the question that, can we take any of these middleware, like let's say Hadoop, come up with a design so that directly it runs with Verge interface. And if the Hadoop can run over Verge interface, then any of your Hadoop application can directly take advantage of that and then trying to deliver the performance and scalability. So in this context, we have come up with two strategies. So one is the traditional Hadoop infrastructure, which uses the HDFS together with its components like the MapReduce, RPC, HBase, all those things, and how we can accelerate that. And the second strategy is to just to use, instead of HDFS, focus on the HPC clusters. Let's say it uses Lustre, and how we can just focus on MapReduce. If you have just MapReduce based applications, can you really run it efficiently on Lustre based test bed? So with that, actually, while we are working on this project, we have also started putting some of these designs together, and I'll give you some case studies. But if you go to this website, so these packages are actually publicly available. So we have an RDMA for Apache Hadoop for 2.x series, also for 1.x series, the RDMA for MEM-HDFS, that is a component, if some of you are familiar, which is widely used in the internet data centers for the Web 2.0 framework. And also, while we are working on these, we have also found out there is a need for some benchmarks, the micro level benchmark, just to see what is happening when you change some HDFS layer, or if you want to just evaluate MapReduce, how you can extract the performance or evaluate it well. So we have a set of micro benchmarks. So if you go to this site, you should be able to download it. The last summer, we started making some releases. So far, we have around like 76 organizations from 13 countries. They're using all these different packages. If you go to the website, you will see all those users. And I'll talk a little bit later, like we have done research on HBase and Spark, but we have not yet put together into the release. That's what we'll be trying to do in the next few months. So this goes into a little bit more details, especially on the Hadoop release. So we have a 1.x, which is based on the 1.2.1, and that has the complete support, like HDFS, MapReduce, and RPC. It supports both InfiniBand as well as Rocky, and it also can be configured to be used on the traditional socket. So you can actually do whatever numbers I'll be showing here. You can yourself do this kind of analysis or evaluation yourself by just reconfiguring it with the appropriate framework. But in the 2.x, so far we have only the HDFS component, which we have pushed out, and we are working on the MapReduce and RPC, and it will be available as an integrated package very soon. So let's see some of these detailed case studies and sample numbers. So I'll basically show some numbers for HDFS, MapReduce, and the Spark. So this shows our overall HDFS design, like how you can take an HDFS, let's say traditionally, it is written with the Java sockets, runs with 1 or 10 gig with IP over IP. So what we have done here is that in addition to this, we take the right operations, and then from this JNI layer, we have done our design, which is written with the verse. In that way, it can actually run with any of the RDMA-based network like InfiniBand or iWarp or Rocky, and it has all these RDMA-based HDFS write, RDMA-based HDFS replication, parallel replication, on-demand connection, InfiniBand Rocky support. So those are the kind of features we put it there. So this shows some sample performance numbers. So let's just you want to focus on just the communication time, like the data is being replicated over the network. So here, what we are trying to show here, like on the same cluster, we have 10 gig, that is the blue line. And this is the InfiniBand, which is the QDR, the quad data rate, which is like 32 gigabits per second. And this one is running with IP over IP, that means the sockets interface. And this is the red line, which is our RDMA-based design. And here you can see that as the data size increases here, we are able to get around like a 30% improvement compared to IP over IP, and around 56% improvement over 10 gig. And these are some of the references where all the design details and some additional numbers are provided. So you are welcome to take a look at those. So those are some micro benchmarks numbers. So here we try to run on some larger scale systems. So this is the DFSIO. Some of you might be knowing that is a very common benchmark which is used to evaluate HDFS. So this run has been done on the TACC-Stampede, and what the two lines, what we are seeing is this, the IP over IP, that is the sockets based design, and this is our new design, which is RDMA based. And here you can see that this was running on 64 data nodes with 1,000 cores. Each node has like 16 cores, and with single HDD, that is the hard disk per node. And here you can see that the RDMA based design is able to push the throughput around 64%, and the latency is able to reduce by around 37%. Now, similar things what we have done with also for the MapReduce. Not only just we have changed the network connections to like the network protocol to RDMA, but internally we have also done a lot of these kind of additional designs like prefetching, caching map output, efficient shuffle algorithms, in-memory merge, and the more importantly, to make sure now, since the communication costs are changing, how do you actually have a good overlap between map phase, shuffle phase, and then the merge phase and reduce phases. So here it shows, like if you take the default Hadoop architecture, you will see that these phases don't get overlapped. Like these phases, 3 phases get overlapped, but they don't get overlapped with the reduce phase. Our last year design, we wanted to put some of these overlap, enhance the overlap, and very recently, we have actually done a very aggressive design so that where all these different things can be overlapped. So means if you can have much more overlap with all these phases, you will see that you will get very good performance. And this paper was presented at ICS conference just 2 months back. So now if you take a look at, these are some of the numbers from 2 common benchmarks, SHORT and Terasort, a lot of people use. So what we are trying to show here, this is the IP over IP number, and this is the RDMA based design. And this is the green line, which is the unstructured data accelerators from Mellanox. I think Brian will be talking a little bit more on that in the next one. So we are trying to show the numbers here. This is on our local cluster. As the cluster size is increasing, we are also increasing the data size. And this is the Terasort on the TACC-Stampede. So again, you can see similar kind of trends here. If you do a 240 gigabytes of sort on a 512 core cluster, we see around 40% improvement here. And here from 320 gigabyte Terasort, again we see around 38% improvement. Now this is another kind of benchmark from Purdue, some of you might be knowing, called PUMA. So it has a set of different kinds of benchmarks, and here again we are trying to show 10 gig with IP over IP and then the RDMA based design. And especially if you see like let's say this self join or sequence count, so these kind of benchmarks or kernels have more communication. And especially the RDMA design is able to really give a good performance benefit here, around 50% improvement for self-join or 49% improvement for the sequence count. Now recently we started working similar kind of things for Spark. So here, just like the traditional the Java NIO shuffle server, native shuffle server, we added a RDMA shuffle server as a plugin. And this also internally has a lot of designs like dynamic connection management and sharing, non-blocking and out-of-order data transfer. So this paper we presented at Hot Interconnect conference 2 months back. And here it shows some preliminary numbers. And this is from the benchmark, which is group by, and that is a common benchmark people are evaluating based on the Spark. And here you will see that even in like a 32 core, 64 core environment, we are able to give benefits like 18% or 20% compared to the IP over IP, and this is the traditional, again, the 10 gig IP over IP and the RDMA design. So those are the kind of things for the native HDFS and MapReduce we have been working. So the second dimension, what we are focusing here, a lot of people want to actually combine HPC with the big data, and we are seeing the similar kind of theme here. So that means instead of deploying a separate Hadoop cluster, so the question is, can the existing HPC clusters, I mean, I showed you some numbers, there are a lot of such clusters all over the world, can we take advantage of those clusters to run like a MapReduce kind of jobs and efficiently? So this shows a very typical architecture of, let's say, any high-end clusters. You will see a lot of compute nodes connected with the metadata servers, object storage servers. So this is the Lustre setup. And if you take a look at each of the node, so that is trying to run the MapReduce jobs. It also has the task tracker and also the Lustre client. So now actually there are 2 choices. So let's say if you have a local disk or you don't have a local disk. So you will see 2 kinds of HPC deployments taking place. So if you have a local disk, so then the question is, can this local disk be used at the intermediate data directory, or if not, can we put all the data to the Lustre? Okay, so these are the two kinds of architectures we evaluated. So this is the first result where the local disk is used as the intermediate data directory, and these numbers are again taken on TACC-Stampede, and this has the FDR, the 14 data rate InfiniBand. And what we are trying to show here, again, this is a 64 node numbers. The data size here we are increasing from 300 to 400 to 500 gigabyte, and the sort. And here we see that compared to IP over IV, which is the sockets level design, the default design, we are trying to get around like 44% improvement. And here on the right hand side with 128 node, we are trying to see again around like a 48% improvement on the 128 nodes. So the next one is like, instead of having the local disk, now the question is we try to put the data in the Lustre, which is the shared environment. And here also we see similar kind of a trend. We see like around 35% improvement, and here on 320 gigabytes, we see around 33% improvement. So these are just focusing on the basic designs where we move from sockets to RDMA. Of course, there are some advanced designs and optimizations we are continuously working on, trying to take advantage of the Lustre features so that we can actually try to deliver you even higher performance than this one here. So continuing with the ongoing work, I showed you this chart a little bit earlier, and so far what we have done is basically taken the sockets to RDMA protocols, and we have touched a little bit of this point-to-point communication, the threaded model, and the I/O and file systems, but there is an entire framework which is left with a lot of additional challenges, and those are the challenges one has to actually solve to come up with the complete design. And not only that, the bigger challenge comes is the upper level changes. Okay, so for example, now based on these numbers, if you see like earlier whatever was running slow, this entire architecture, the Hadoop architecture has been designed with slow network in mind. So now if the network becomes faster, we need to ask the question saying, can we modify the architecture at the top layer so that we can even get higher benefits? And the other challenge is, we see that while we are trying to do this design, we found out that there are no real micro benchmarks to evaluate these low level designs. Everybody just focuses on Terasort kind of thing. You can get those numbers, but you don't know where the benefits are coming from. So that is also another focus in my group. We are trying to not only design these micro benchmarks, but also trying to establish correlation with the application level benchmark, so that we know that where the benefits are coming and where things are getting hurt, so that you can tune the designs appropriately and then get the maximum benefits and scalability. The other features are like here, can you combine some of these different kinds of designs? Like I mentioned earlier the Hadoop, which is the HDFS, similarly MEM-HDFS, which is being used for a lot of Web 2.0 architecture. So the question is, can you actually combine it? So here, let's say there's an in-memory I/O and replication. Can we accelerate this with HDFS with MEM-HDFS? And this is an initial design. This is not RDMA based design, just simply been taking basic HDFS and basic MEM-HDFS, and can you combine to get bigger benefits? And here are some sample numbers. We'll be presenting this in the Big Data conference in 2 weeks. And here it shows like just by combining some of these components, you can push the performance benefit. Like this is the default HDFS and this is the MEM-HDFS based HDFS. You can get like a 2.6 improvement. And if you, in the test DFSIO, if you do like random writer, you'll get around 38% benefits. So these are our like the future plan on the OSU HiBench project. As I indicated, like our upcoming releases, we'll have the Hadoop 2.x with MapReduce and RPC, the Spark, and HBase. HBase, we have done all the research. We have a lot of papers, but we have not taken the things into the distribution, which we'll try to do. And then also all these micro benchmarks, again, we have worked out. We have the publications, but we just need to package them and then push it out to the public. And then, of course, the advanced designs with upper level changes and optimizations. So with this, let me conclude the presentation here. What I discussed here, some of the challenges in accelerating the Hadoop and Spark. Presented some of the initial designs, and these results are very promising, but of course there are a lot of other open issues which need to be solved. And if we can actually solve all these open issues and put them all together, then we can see that will be able to enable the big data management and processing community to take advantage of these modern HPC technologies to solve all our big analytics problem. So these are all our pointers. Once again, if you have not used our RDMA-based distributions, or if you want to experiment with it, play with it, please feel free to download and let us know how it works with your applications, and we'll be very happy to get some feedbacks from you people also, trying to enhance it further. If we get some feedback from your applications where it works and where it doesn't work, and we'll be very happy to work with you. So let me just stop here. If there are any quick questions, I'll be happy to take. Yes.
Wait a minute. Many thanks, TK Panda. And we have time for one question.
Thank you very much for the interesting talk. The numbers sound very promising. I was wondering, have you submitted those changes to the Apache projects? And if
No.
so, what has been the reaction in the community?
No, not yet. So this project is still in its very infancy. So we are still trying to tune all these things, and once it gets matured, we'll be happy to push it into the Apache. That is our future plan, but it has not been done yet. Yes.
Thank you for the talk. It was fantastic. So, two questions. One is, do you guys support other releases of MPI too? So, Intel MPI, can Intel MPI and other MPI versions be supported with the HiBD? So, is it closely tied to MVA pitch?
No. I think you got confused. No. These two are separate things. The MPI stack is separate. I just showed some numbers. Okay. Yeah. As a reference.
Okay.
So these hybrid things are totally independent of any MPI. Okay. They are self-contained.
Okay. And if I get the model of the release right, so we can just use our configuration on your release, and this might start working. Is it the model that I understand, right?
Yeah. You should be able to download. So exactly, if let's say we keep the API compliant. Okay. So let's say it's the 2.x series, 2.4.1 base release. So if you have any applications which is conforming to that 2.4.1, it should directly run.
Okay. Thank you very much.
You don't need any changes.
Okay.
Final question for this talk.
Yes.
I was just a bit surprised that most of the numbers lie between 35 and 40%. So if you'd analyzed the network stack from a theoretical point of view, would you have been able to predict the outcome?
It actually depends. We try to do some of these in the paper, but it totally depends on your storage and I/O subsystem. Okay, so these are the numbers I showed, like only from 3 clusters we have taken: our local cluster, Stampede, and some SDSC Gordon. If you take some modern systems, like let's say people put a lot of disks together, okay, these numbers will change. Okay, we have not done, like we don't have access to all those kind of environments, like very high end, like putting 32 disks kind of thing, hard disks or SSDs. There you may be able to see much more benefit, but it's not like plateauing it out kind of thing.